Hello, welcome to Ionic Compounds Notes. Today we're going to be looking at how two atoms combined in an ionic fashion. So for a review, we can think about oxygen, aluminum, and phosphorus ones. We want to write electron dot structures and then predict what ions are going to form. And go ahead and pause it and give that a try. Great job, you got it. Yeah, oxygen is going to have 6 valence electrons, which means it's going to form a 2- ion by gaining 2 electrons. Aluminum's got 3 valence, and so it's going to lose 3 valence electrons to make a 3+. Phosphorus has 5 valence, and so it will be gaining 3 electrons to make a 3- ion. So we've got the oxide ion, the aluminum ion, and the phosphide ion. So now we're going to think about how that happens, because electrons just don't disappear. They have to go from somewhere to something else. They can't, if one of them gains, then another one has to lose. If one loses, another one has to gain. So when we think about an ionic compound, we're going to need one that's losing, that's going to be a metal, and one that's gaining, that's going to be a nonmetal. So you've always got a positive cation and a negative anion. And even though you always have a plus and a minus, the thing is, when we add up the total, the compound as a whole is going to be neutral, which means for every positive charge, we're going to also have a negative charge. And so we want to think about how that works. For example here, lithium, which has 1 valence electron, is going to lose its valence electron, but fluorine right here is going to gain that 1 valence electron. And so lithium is going to now be a 1+ charge, and fluorine is going to be a 1- charge. And that works out pretty nicely because you got a 1+ and a 1- charge, and so they're pretty much even. And so we've got overall, it's neutral. And the thing is that now this positive ion is going to be attracted to the negative ion. And that attraction between ions is what we call an ionic bond. And so the bond is the attraction between those ions. We might call it an electrostatic force. They have opposite charges and opposites attract. Remember that in an ionic bond you have one that's giving and one that's taking. So the anions are really, they're kind of stealing the electrons from the cation. They're not shared at all. And so we can think about these, that we can write a chemical formula for that last one. It was 1 lithium ion was with 1 chlorine, and so we'd write LiCl. Or likewise, we can do sodium and chlorine is sodium chloride. When we talk about this, a formula unit is the lowest whole number ratio of ions in an ionic compound. Let me show you what I mean by that. So this here, if you look at the picture, is a model of what a salt crystal, sodium chloride, might look like. It doesn't mean that there's 1 sodium bonded to 1 chlorine. What it means is that every positive sodium is going to have a whole bunch of chlorine, negative chlorine sticking together, and they're going to form this big crystal. But in here, it's a 1-to-1 ratio. For every 1 sodium, there's 1 chlorine. And that's what we mean by a formula unit, is it's the lowest ratio of ions in a compound. And so we can think about sodium has 1 valence electron. It's going to be transferred to chlorine. So sodium would make a 1+, chlorine would be a 1- chloride, and so because it only takes 1 of each to do that, that's going to be a 1-to-1 ratio in the formula unit. But if we think about one like magnesium oxide here, we could see, okay, well, magnesium's got 2 valence electrons. It's going to give away 2 electrons. Likewise, oxygen has 6 valence electrons, so it's going to gain 2. And so 1 atom of magnesium with 1 atom of oxygen is going to go in a 1-to-1 ratio for magnesium oxide, MgO, a 1-to-1 ratio. But what about calcium with fluorine? Calcium's got 2 valence electrons, where fluorine has 7. So this calcium can give 1 away here, but then fluorine's got 8, so this atom is done. It's not going to gain anymore, even though calcium's got another one to give away. So what will happen is this extra electron will be given to a different fluorine atom, which means it takes 2 atoms of fluorine for every 1 atom of calcium. And so we see that calcium becomes a 2 plus, each fluorine becomes a 1 minus. That's what we mean by neutral. 2 plus, 1 minus, 1 minus. A total of 2 minus. So the positive and negative charge is overall equal. We're going to write the formula like this. Calcium, we don't write the 1. It's kind of like writing 1x in math. You don't have to write the 1. And then F2. We use that subscript there to say how many atoms are bonding in what ratio. So 1 atom of calcium with 2 atoms of fluorine. Okay, you try. See if you can figure out, first, how many valence electrons do each of these have? How many are they going to give away? And then how many of each type of atom do you need in order to make it work so that they're giving away the appropriate and gaining the appropriate number of electrons. Give them a try. Yeah, nice job. So you got potassium has 1 valence and iodine has 7, which means it's going to work out perfectly. 1 potassium for 1 iodine. We call it Ki, potassium iodide. Magnesium has 2 valence, chlorine has 7. So that means that one of the electrons from magnesium can go on to a chlorine, but you're going to need a second atom of chlorine to take the other electron. So we're going to end up with MgCl2. 2 atoms of chlorine for every 1 of magnesium. Finally, potassium has 1 valence where oxygen has 6. So oxygen needs to gain 2. It can get 1 from a potassium, but in order to get a second electron, you need a second potassium. So that's going to be K2O1. You don't have to write the 1. So K2O would be our formula for that. As we think about these, we can start to think about some properties that they have. The biggest idea is that these ionic bonds are forming this crystalline structure. And so we see these kind of crystals. You can see right here's some crystals. They get kind of neat in there. They have pretty high, like really high melting and boiling points. And so that's because we have all these bonds. It's not just one sodium bonded to one chlorine. It's this chlorine is bonded to all different sodiums. And there are lots of bonds in there, and because of all of those, it takes a lot to get these to move around each other or boil off. They're going to conduct electricity if they're dissolved or melted. So if we were to dissolve it in water, that would split these up into ions. We would have our ions separate, and so the ions could move to carry electric current. Or if it's melted, we would melt these down so they can move around and be able to carry that charge or current. They don't really burn at all because, well, there's lots of bonds in there and they don't really react much. They're already pretty stable. The ions themselves are quite stable. But when they get there, they're going to give off a lot of energy in order, when it forms from a kind of, like, think about sodium metal and fluorine gas. Those are both very reactive, and so to become the ionic compound, it gives off a lot of energy because they're going from more unstable things to a very stable ionic compound, which we call a salt sometimes too. Any salt is an ionic compound. So big ideas is they have, again, these 3D patterns, 3D crystalline structure. That's what makes them have these properties. Because of all the bonds that are in that 3D arrangement. And so, again, here you got your chlorine, this sodium. This is just a pictorial way of showing what I've got with the model here. Have a great day, and good luck.